So today we're going to start talking about the highest level of math you're going to see on the ACT. Today we're going to talk about imaginaries and logarithms. And next week we're going to get into a couple other topics, including trig. If you have not seen these before, that's okay. We're not expecting you to. About half of you have, and that's great. For those of you who haven't, I would suggest that you come back after you learn these topics and watch these videos again, because you will have access to these eventually. And check it out and see which different types of problems will be on the ACT. So first up, I'm going to start on the lower right here. They may just ask you to simply add imaginaries or complex numbers. If they do, you add the like terms. So 3 plus 2 is 5, and 2i plus 5i is 7i. Great, I'm done. So it's just combining like terms with I until you start multiplying them, and here's why. Square root of -1 is I, or imaginary. We know we can't have roots of negatives. However, we can talk about the letter I, because if I have I squared, that's the same thing as -1. So anytime you're multiplying two complex numbers together, you're probably going to get an imaginary somewhere. So let's see where that comes from. 3 times 5 is 15. 6i, great. Minus 10i, still nothing of interest until I get to the minus 4i squared. Minus 4i squared is actually the same thing as plus 4. The reason that it's plus 4 is I squared is -1 times a -4. That makes that positive 4. So anytime you see I squared attached to a constant by multiplication, all you're going to do is switch the sign and the i's go away. So that leaves me with 19 minus 4i. So that's one type of imaginaries problem you're going to see. The next type is the I to the. And the I to the is going to be, in this case, like I to the 36. They're going to ask you, what is that? I, negative I, 1, or -1. So how you do that is any I to the 4th power is 1. That also means I to the 8th, I to the 12th. I to any multiple of 4 is 1. So since 36 is a multiple of 4, my answer is 1. Great, that was easy. How about 57 though? I to the 57. I need to find the largest multiple of 4 before you get to 57. So if you sit and think about it for a second, well, 4 doesn't go into 50. It does go into 52, which means it also goes into 56. Hey, that means I to the 56 is the largest multiple of 4, and that would have one I left over. Since I to the 56 is a multiple of 4, I know that's technically the same thing as 1 times my I to the 1, so my answer is just I. So those are the two types of imaginary problems you'll see on the ACT. It's very rare to run into others, but always possible, so brush up on your imaginaries before you take the test. Logarithms are the other large topic we're going to talk about today. A lot of information in logarithms. Let's get down to the basics though. The basic idea is if you see a logarithm, and we'll say log instead of logarithm, whatever the base is, in this case b, would go to the other side, and y would become the exponent, and that's how they get this b to the y business over here. So if you see something like this, log base 7 of 343 is 3. The reason that is because 7 would go to the other side, and 3 would become the exponent. So 343 equals 7 to the 3rd, which is a true statement. It's not really a problem there, just true. So let's say they ask you a question and they say log base 4 of 64. First, if it doesn't equal anything, we want to set it equal to something. In this case, I choose x, but you could choose j or heart balloon or a pokeball. It doesn't really matter, but what I need to do next is convert the log. So 4 goes to the other side. X becomes the exponent. So my question now is 64 equals 4 to the x. So I need to come up with an answer for 4 to the what power is 64. In this case, 4 to the 3rd is 64, so my answer is 3. So if you're familiar with logs, they're also going to throw the properties at you, but they won't be in a super difficult setting. So the 3 properties I'm referring to are if you have a power on your thing behind the log, in this case my r, you can drop that out front. So if I have x to the r for a log base b, that means I could drop that r out front. You can also go backwards. I could bring that r up and make it the power on the x behind it. Next is that multiplying stuff behind a log is the same as adding them individually. So here I have x times y. which is really the same as log x plus log y individually. They get their own log. If adding logs individually is the same as multiplying, then subtracting logs individually would be the same as dividing. So let's see how they might use that. So here's the first problem. All we need to do is if you have something multiplied out front, you can bring it up and make it the power on the object of the log, whatever is behind the log. So that would make that log base 4 x to the 5th equals log base 4 of 32. If you do know what logarithms are, they won't make them any more difficult than a log equals a log. So now I'm saying x to the 5th equals 32, so I need to think about that for a while. And 2 to the 5th is 32, so that's my answer too. Last example would be, again, everything has a log. Very rarely will you see log equals a number with these properties problems. So subtracting logs individually, we said, was the same as dividing them together. And since log equals log, I can remove these log base 3's, cross multiply, and get 9. So my answer is 9. Very tempting on this one to just cancel out all the logs and say 36 minus x equals 4, and then say 32, which is going to be an available answer. That is a big no-no. Bad, don't do that. Make sure you understand that subtracting is dividing, adding is multiplying, and something multiplied out front is the same as making it as the power.